Good morning, everyone. Oh, this works. Good. So I'm Igor, this is Christophe, and we're going to talk about Powder Keg. So let's start with introducing where the Powder Keg came from. Hospital Corporation of America is, well, huge. So we have about, hundreds of facilities covering 20 states, basically the biggest healthcare provider in the US. And with all of this size comes a lot of data. So a couple of years ago, a unit was created in HCA with the purpose of basically sciencing all this data. And as any data scientist will tell you, 90% of the work is basically data cleaning and then a little bit of PhD math on top of it. So with all the data and all the janitorial work, we ended up gravitating towards some sort of big data solution and then ended up with Spark. Now, for those who don't know much about Spark, many years ago when Hadoop platform appeared, it turned out that Hadoop MapReduce was a little bit slow. So there became a big competition for finding the next big performance solution, and by providing an in-memory computation platform, Spark succeeded in winning hearts and minds. The key API for Spark is an RDD, the resilient data set. Now, the data set part is simple, that's your data. The distributed part means that basically all your data is spread all over the nodes on your cluster and hopefully computed locally there. And the resilient part comes from the fact that the information about the transformations you're performing on your data is stored within the RDD, and in the case of failure, everything can be recomputed. So in practice, it works like this. We have two types of operations that are performed in RDDs. The first one is a transformation, so something like map or filter, they comprise the RDD, and then you have something like an action called, in this case, for example, a group by. What happens in practice is for the transformations, they are performed locally, so in this case, we're looking at a cluster of 3 nodes, and map and filter, everything happens on each node. The data is not passed around, and everything is nice and quick. But as soon as you get to an actual action, for example, group by in this case, the RDD is realized, so the calculations are performed, and then the data is shuffled, and the new RDD is created. The shuffling part is actually quite expensive, and a lot of Spark performance problems will probably end up from you not very carefully arranging your operations in such a way that you have as few actions as possible, or at least grouping most of your transformations together. So if you tried to use Spark and Clojure before, you probably know that there are some excellent libraries out there. We have Flambeau and Sparkling. Both sort of started from some work by Climate Corporation. And we use both of them with some success. But overall, the underlying Java API was a little kludgy, and it kind of translated to making work not particularly comfortable. So what I mean by that is, in plain Clojure, if we try to square some numbers, we don't really need to do much. We start with a collection, throw a transducer on it, and we're done. Now, as soon as we move to Spark, it gets kind of weird because, first of all, you have a lot more code. Second, if you notice, they have redefined some core Clojure functions, like function or map. And on top of all that, you also have a problem that you have to AOT all of your code. So you have to compile all of this to run. Now, if we step back for a second, what Spark really is, despite the Java API, is a way to describe operations on data. And in Clojure, we have this thing that is supposed to describe the essence of a transformation on data, regardless of the inputs and outputs, which happens to be transducers. So can we run transducers on Spark? Can we do it in such a way that we don't have to AOT everything? And can we do it without trying to rewrite most of the Clojure in Spark? As it so happens, we could. So Christophe will explain how we got there.
Yeah. So we made a proof of concept, and the proof of concept was being able to run this code, the last line, where we just define an RDD function which takes an input, a transducer, and creates the corresponding RDD. And so when you do that, you don't have to learn about the semantics, about new map function, a new collect, a new filter, and so on. You just reuse the knowledge you have about the Clojure core API. And sadly, it was rather easy to get it working while we were running Spark in local mode. Local mode is fake Spark. Basically, it's Spark running with your application inside a single JVM. So you share everything. It's not distributed at all. Most of the difficulties are not there. And this is why with Flambeau or Sparkling, you can have some REPL experience, but you have to stay in local mode. You can have the REPL experience against a real cluster. And this is really what we are after, because we didn't like all the bad surprises which occur when you migrate from the local mode to the cluster. And we also wanted to enable people to do some exploratory work with the real data sets on the cluster. So to get stuff to the cluster, you need to send classes, and that's why you need to AOT, usually. But something gave us hope. There's a Scala REPL for Spark, and the Scala REPL works against a cluster. So we looked into how the Scala REPL managed to send its classes to the cluster. But sadly, it's very specific to Scala, and we can't reuse that for Clojure. Plus, it uses some semi-protected stuff, so it wasn't a good option. Luckily, there's something in Spark which is pretty useful, is that you can extend the class path of a running application. You can add new stuff on the class path. And you do that by providing a jar and adding it to the application where it runs. So now the goal was to get all classes that were defined dynamically at the REPL, package them into a jar, and send the jar across the cluster to the workers. But to get to the bytecode of the classes, we have to ask for the bytecode to the Clojure dynamic class loader. And there's no facility in the Clojure dynamic class loader to get to the bytecode. So one option would have been to fork Clojure so as to expose this facility into the class loader. But we weren't keen about forking Clojure and maintaining our own fork, even if it's half a dozen of lines. So we thought about a Java agent. A Java agent is a process which connects to a JVM and gets full access to all the bytecode and can read it and even modify it. So we looked into writing an agent. It turns out that you don't have to have a separate process. A JVM can be its own agent. So we created Ouroboros, named after the self-devouring snake. And it's just a very simple agent which connects to the JVM and exposes the powerful instrumentation object to the REPL. So once you get a hold on this object, you have full access to any class. You can patch code, you can do anything. And so now we can get all the bytecode of any class, package them into a single jar, and send it across the network. And boom, now this works on the cluster. But sadly, we were so focused on getting the classes over to the cluster that we forgot about namespaces and vars. So while the first one works, this doesn't work. The first one, the transducer, is the only thing which gets transferred to the worker. And the transducer has no dependency on anything but Clojure core. And Clojure core is always available because the loading of Clojure core is triggered by the static initialization of Clojure classes themselves. And so now we have to find a way to transfer the state of the namespaces and the vars to the cluster. So we went for a very naive approach. We walked through all the namespaces And inside each namespace, we look at each var, we capture the metadata, the value, and we build a big map representing the whole environment. There are some knobs to control that. There's a blacklist to not send some namespaces, and you can opt out of the transfer by putting some metadata on the vars. But generally, the idea is just to create a big map, big immutable representation of the whole environment, send it to the worker, and have the worker recreate it on the other end. And now, this works. But we need to do this each time that we want to send something to Spark. So the first approach would have been to diff the two namespace snapshots and send only the diff. But thinking a bit more about that, we realized that since we have Ouroboros already connected, we can just add instrumentation to Clojure long var so as to be able to be notified when a var is created or modified. So we don't have to traverse the environment over and over. We just keep a log of the modification to the vars, and we send this modification log to the cluster. So now, for a quick demo of the basics, I give the keyboard to Igor.
Okay, can everybody sort of see this? Yes?
Bigger?
Okay. So, we're in our regular REPL. Let's start by importing keg, or powder keg. Okay, so what happens here, as you can see, it starts Ouroboros and instruments itself, collects all the Java classes, and plugs into Clojure var. So at this point, let's connect to an actual cluster. Now I'm going to start a cluster locally with 3 nodes. Okay.
Exclamation mark.
Oh. Okay, as you can see, it is now sending all of the jars, all of the classes, packages them in jars and sends them over. So let's start by creating an RDD. Now this is fairly simple. We take a Clojure collection and make an RDD out of it. And what happens here is, as you can see, it again shipped the local context to the cluster in a jar. And it is, in fact, a regular Java RDD. So we can use Java APIs on it, like this, for example. And voila, that works. But this is a little convoluted, and we could do this in a little more Clojure way. So let's use into. And now we're going to use our first transducer on it. So let's do take. And we are operating on the same RDD. And there that works.
Or you could even just do into on the RDD, because RDDs are reducible. So you can just reduce or into on them.
So with that working, let's try something more complicated. For example, the example we were looking at a second ago. So again, we start with into to be able to actually see the output. We create the RDD. And we're going to apply a transducer directly to it here. So keg RDD allows you to apply transducers directly. So let's do the square example. And there you go. That works as well. But the example that actually was giving us trouble is the one with local namespaces. So let's redefine multiplication. And instead, use our newly defined multiplication here. Sorry.
Yeah. You multiply. You just pass one argument to multiply.
Sorry. There you go. That's better. Now here's something more interesting. If, for example, we have redefined it here, it still picks up the change to it. And we can see that. Now, the plain RDD is just one of the available RDDs. There are, in fact, other types of RDDs, and they have their own challenges.
Okay. So much of the time, to do something useful with RDD in Spark, you are not going to stay with plain RDDs or items. You are going to use key-value RDDs. Key-value RDDs are just RDDs which happen to hold pairs, but not any kind of pairs. It must be a Scala tuple 2. And so it means that your code then would have to deal with special accessor function and constructors to get to the value of the tuple and to create tuples. And this is something that we really didn't want to have to do. We didn't want to expose any kind of, or as little Spark or Scala as possible. And so when you have a map entry or a two-item vector, it's going to be automatically converted into a tuple 2. And when you have an RDD of tuple 2, it's going to be converted on the fly to map entries before being passed to the Clojure code. All this conversion may seem a bit inefficient, but most of the time it's not even going to occur. But first, to explain how this works, we have to make a detour through another library. So Xforms is a library that I started before working with Spark. And in truth, the whole lineage of Xforms is rather old. I always had this pet function of mine, reduce by, which is like the offspring of group by and reduce. Instead of group by always produce a vector, and sometimes you don't want to have group by do the big vector, and then post-process the vector to reduce it. So often I had the need to have a reduce by so as to be able to perform the grouping and the reduction in one step, in one pass over the data. And when transducers were introduced to Clojure, I thought to myself, okay, I'm going to create transduce by key now, or transduce by. And working a bit more with transducer, I realized that I was really missing a for transducer because I use and abuse for in my code, and when I wanted to convert some sequence code using for to transducer, I have no option but rewrite that with mapcat and so on, and it was painful. So I started Xforms for and for what was originally transduced by. So for is really just like the regular for, except that the first collection expression is replaced by a placeholder %. And so to rewrite a regular for to a transducing for, you just replace the first collection by % and put the collection below. But it's rather simple. And transduce by, I never wrote it. Because then I realized that with transducer, it was possible to do something better than transduce by. It was possible to define an higher order transducer, by key. By key is a transducer which takes another transducer as its argument. And the simplest example of by key is mapvals. Mapvals is just a function which apply another function to each value of a map and return the map of the transformed values. And so the only thing that you do is you specify by key map f. And so the job of by key is to take the pair, to take it apart, pass the value to the nested transducer, get the transformed value back, pair it back with the key, and emit the key. So it allows to express mapvals in as a one-liner. And what is interesting is that by key spawns several concurrent transductions. So you have several transductions going on, one for each key. So for example, if you have a stateful transducer like into, then you are going to perform one transduction for each key, and this gives the ability to redefine group by just saying that you are going to group to consider kfn to provide you the key. So you get the key, you get the original value, you pass the original value to the transducer which is into, which is going to accumulate them into a vector. And so you have several accumulations going on, one for each key. And at the end, all the accumulations are completed, emitted back with the result tagged with the original key. And you get this definition of group by. And similarly, you can define frequencies pretty easily, or sum by, and sum by is typically the kind of stuff that I would have written with reduce by before. And using by key, you can easily write some code to perform some roll-ups or all kinds of aggregation and have it to be performed in one single pass over the data. And since XForms was really a lot about dealing with key-value pairs, I took some inspiration from reduce KV. Reduce KV expects a reducing function which takes 3 arguments instead of 2. It expects the key and value to be passed as discrete argument to the reducing function instead of as a pair. And so I generalize it in XForms. I have a KV REPL protocol which allows functions to declare that they are ready to take 3 arguments. And most of the XForms transducers know how to deal with KV REPL function and produce also KV REPL reducing function. So when you create a transduction on pairs with XForms, most of the time you don't even allocate a single pair. And this is how by key, this is how in Keg we managed to avoid the conversion from and to tuple2. Because at the start, we take the Scala tuple2, we split it in 2, and pass it a discrete argument all along the way of the processing, and only at the end, we recreate a single tuple2. So we don't allocate much pairs. We even, in some cases, allocate less pairs than Scala code. And so there's another function in Keg, which is by key. By key is just a specialized version of RDD, which is going to ensure that the data is partitioned, because when you use RDD, the data is segmented into several parts, but it's purely sequential. It's not meaningful. when I say that by key ensures that it's partitioned, it ensures that pairs that share the same key are collocated on the same node. And so that's the job of by key. And so by key either take as an input an RDD or a collection which already has pairs in it, or it can take a collection and RDD of random item and key them on the fly. This is what is done in the second example. And so by key by key may accept a transducer too, and the transducer is going to be executed for each key, like for X by key. The same logic as with the by key of X forms. So here, the first example is just we take a range of 100 items, we group them in odd and evens, and we sum them. And so this is going to create an RDD, perform the sum on each node, then shuffle the partial sums and end the sum at the end. But if you followed closely, you notice that we perform the sum twice, once before the shuffle and once after the shuffle. And it's not always that easy to perform exactly the same computation on the two sides of the fence. And so what we have is the opportunity to specify different transducers to use before and after the shuffle.
So let's take a look at how all of this works. Okay, we're back in our REPL, and let's start with something simple. Let's create an RDD out of a map. So we created the regular RDD. Now, what we were talking about with regards to partitioning is this. As you can see, it says that there is no partitioner. What this means is that this is default partitioning, and it hasn't actually reallocated the data with accordance to the key. So if we do keg by key and run it against the RDD, you can see that the partitioner is now actually assigned, and the data has been shuffled. So let's look at more functionality of by key. So we start by creating an RDD again of 100 things, and we're going to try to key them by modulus 7. So what this is going to do is take all of these 100 numbers and assign them a key value. And this created a new RDD, which we can look into. There you go. Now, this is the basic functionality. Let's take a look at what happens with transformations. So we start with a little smaller RDD, and we are going to key it with odd, so separating into odd and even numbers. And then we're going to use X forms to reduce and sum them. As long as we import X forms, of course. Okay, let's try this again. Now notice that here we're putting that into an actual map. And there's the calculation. Now this is a happy path where summing things on both sides first before shuffling and after actually works better, because you can get the sums on each individual node and then you're just summing up the results. But if we do something like this, you're going to be in trouble. So let's take a look at this example. We start with a map RDD. And we're just going to increment them. And as you can see, we have a bit of a problem because we started with 1, 2. The increment should have produced 2 and 3, but we ended up with 4 and 3. So what happened is that we incremented it first before shuffling, and then we incremented it again. Now, to fix that, there are a couple of ways to doing it. First of all, you can say that we only would like to perform this calculation either before or after. And both of those work. Or we could actually shuffle the RDD before applying the calculation. So you can do this. By pre-shuffling it. There are also a couple more knobs on Keg by key, which you can explore later in the API. Now, we can actually use all of these options together in some meaningful ways. But before that, what kind of Spark demo would this be without the favorite word count? So this is the word count, this is Scala, as picked off from the Spark homepage. This is the exact same re-implementation of it in Keg. So as you can see, we start out by assigning a Spark context to a file. The Spark context is available in Keg. And then we're going to mapcat it, splitting up the words in each individual line. Then we're assigning 1 to each word to give it some value, and then we reduce it and sum it up. Now, the one problem with this that you would think would have is that we're assigning 1 to every word for some reason, instead of actually summing them up in progression. So with the advanced functionality of by key, we can, in fact, avoid this allocation of tuple 2s that are going to be just thrown away by first keying by identity. So it's the same thing. We create for each individual word, it's assigned a key. But instead, we're using one of the X-form transducers that will allow to count them as they are assigned on each of the partitions. And then when they are aggregated back after the shuffle, we just sum them up. So let's see if we can get that to work. So it's the same code. I'm just using collected works of Shakespeare. And we have created an RDD out of it. Now we're going to use a transducer again to take a look at the results. And there you go. Okay. There are some other APIs provided as well that are not covered by standard Clojure functions. So we have, for example, join, where you can perform inner join, outer join, left join, right join by assigning the default values. There's also group by and a few other things available in the Powder Keg. So what's next for Powder Keg? Well, we're developing streams, and there's some work completed, but there's still some things to sort out with windowing of the actual streams. Also, data frames were introduced in Spark, and we haven't looked at those. So if anybody's interested in starting working on those, that would be very much appreciated. And we have not tried to migrate it to Spark 2.0 yet. But the most interesting application is to take Ouroboros and try to use the same infrastructure to be able to execute Clojure code in other places, like, for example, Amazon Lambdas. So hopefully we'll be able to spin off that into a separate library, and then people can pick it up and start working from there. So if you're excited, if you'd like to play with it, it is available on GitHub, HC Data Lab Powderkeg. And one more shameless plug. If you're interested in Music City and you like Clojure, then come talk to any of us, and we'd be hopefully happy to offer you a position working for HCA. Thank you very much.